Hello and welcome to a new session with edupediaworld.com, your favorite portal for online education. Today's session we will take up some of the topics of statistical quality control. To begin with, we will see some of the tools, and the most important tool in the hands of a quality inspector is the control charts. Now, what are control charts? Control charts are basically graphs drawn to see if a process is functioning within its normal or common limits. If the process is functioning within the limits, fine, and if not, if the process has strayed out of the limits, an quality inspector gets to know about it immediately and the process is stopped and the corrective measures are taken. Now, how these control charts are drawn, we are going to learn exactly that. But before taking up an example, let's understand that control charts are basically of two types. Control charts of attributes and control charts of variables. When we measure a variable, for example the thickness, length, height, weight, volume of a process, we call it a control chart of variables. There are two types of control charts for variables. One is the X bar chart or the mean chart, where we measure the mean or the average of these variables, and another is the R chart or the control chart of ranges. Range is the difference between the maximum and the minimum value of the sample taken. Similarly, we have got control chart for attributes, where we have the P chart or the proportion chart and C chart or the number of defects chart. To start with, we will take up the control chart for mean or the X bar chart. So let's take a sample question and see how to draw a control chart. Well, we have a question here taken from a company which is involved in filling up of bottles with soft drinks. A quality control inspector at the Coco Fizz soft drink company has taken 25 samples with 4 observations each. We do have these samples on an Excel sheet because it will be easy for the calculation. We will quickly switch over to the Excel sheet after overseeing the questions. The data and are of course shown on an Excel sheet. As I have told you, the standard deviation of the bottling operation is 0.14 ounces, and we are asked to draw a control limits of 3 standard deviation for the bottling plant. Now, what is this 3 standard deviation? Well, we know that in a normal distribution, if this is the mean, and if we go 3 sigma on, that is 3 standard deviation, sigma stands for, this is 1 sigma minus, this is 2 sigma, this is the mean, 2 sigma and 3 sigma. We know that if we cover 3 sigma on both sides of the mean in a normal distribution, it covers 99.74%. Therefore, we will have the defects only in this region, which is 0.26%. So here we are asked to draw the 3 standard deviation limits. So let's quickly switch over to an Excel sheet where our data is and see how to draw. Well, as given in the question, we have got 25 samples here taken from this bottling plant, and each sample has got 4 different observations. Now probably the process was designed to fill 16 ounces, but we see that there are slight variations, as we know that variations are inbuilt, and it is not possible to get any two product exactly identical in any process. But what we need to see is that the process is not straying away beyond a normal value. What will happen if we end up filling a lot of extra liquid in each bottle in order to have a good quality and satisfy our customer? Of course, when we fill extra in every bottle, the liquid comes with a certain cost, and we will end up spending more amount of money in the process than getting the return. Similarly, what if we go below 16 ounces every time? Well, that will be considered as a defective. But if it is very minutely below or above, it's accepted, and that acceptable limits are called the normal limits, which we are going to draw. Now here what we do is, as this is an X bar chart, we first find the X bar, that is the mean or the average of each sample. That is, we will find the average of these 4 observations, and in an Excel we can directly find the average using the command average. Okay, so here the average of these 4 observations are 15.91. Similarly, I'll have to calculate the averages of all the 25 samples. So let me just drag this down to here, and here we have the averages. Okay, now we will calculate the X double bar, or the mean of the mean. Let me call it as X, or let me first calculate the total of this, and that happens to be the sum starting from the first to the last. Yeah, and the average of the average, let me call it as X, say bar X double bar, and that is this value divided by 25, as we have 25 samples, and that is 15.95. Okay, now how to calculate the upper and the lower limits? In a control chart, as I said, that control chart is a graph. In a control chart, we have the central line, and this central line lies at the average of the average, and in our case it is 15.95. so this is at 15.95, and then we have the upper and the lower limits. The upper limits, here we call it as the upper control limit, and we have the lower control limit, Now we have the central line at X bar. We have the upper control limit. The formula is the mean plus Z times sigma X bar. Similarly, the lower control limit, the formula is X double bar minus Z times sigma X bar. Now what is Z here? Well, it is mentioned in the question that Z is the standard normal variate. Standard normal variate, and that is 3 in our case, in order to cover an area of 99.74 percentage. So Z here is equal to 3. And what is this sigma x bar? Well, we know sigma stands for standard deviation, and sigma x bar is actually the standard deviation of the sample. And how do we calculate it? We have the standard deviation of the process given here as 0.14, and we have taken a sample of 4 in each. We have taken 4 observations in each sample, so n is equal to 4, and sigma x bar, which is the standard deviation of the sample, is nothing but the standard deviation of the process over n, root of n. Okay, so now we can go back to the Excel and calculate these values. So let me write here n. We have n equal to 4. Let me write that here. And then we have of course this value of sigma. Let me write it here, sigma, or the standard deviation of the thing, which is 0.14. And if I have to now calculate the sigma of sample, let me put it this way, sigma of sample, or just let me write it as standard deviation of sample, and that is equal to this 0.14, that is the standard deviation of the process, divided by square root of n. Yeah, so the standard deviation of the sample is 0.07. now this x bar is of course our central limit. Let me put that here, CL. Now we are ready to calculate the upper and the lower specification limits. So my upper and lower control limits. Upper control limit will be equal to my x bar, that is 15.95, plus z in this case is 3 times standard deviation of the sample, which is 0.07. There's something wrong in the formula. Let me just have a look. 3 times, yeah, it's fine. Okay, well, let me put this in parenthesis. Yeah, so this is the upper control limit is 16.1569. Similarly, the lower control limit can be calculated in the similar way. It's x bar, that is 15.95, plus, sorry, minus this time, minus 3 times 3 multiplied by the standard deviation of sample, which is 0.07, and this happens to be 15.73. so the values are 16.15 and 15.73. Let me put that here. This is 16.15 and this is 15.73. yeah, 16. Of course, we are just rounding it off to the 2 values, and now we are ready. This is our control chart. Okay, so if any value falls within these two limits, 16.15 and 15.73, then it is set to be in control, and if a value goes beyond these two, then it is set to be out of control. Yeah, so now we are ready to plot the data which we have here on this sheet here. So we will of course take the averages of each sample and see if all of these are in the control limits or not. So instead of, we can of course plot them. 15.91, the first one should be here. Next is 16 should be here. The third is 15.92 again here. Next is 15.93, very close to this line, so we see that the process is very close to the central line. Next is 15.98, 98 will be here, and then 16.03, 16.03 will be somewhere over here, and so on. We see that most of these are, I mean, we can just have a overview here, and we see that they are in control. So we see that they will all be falling somewhere around this central line, and so we say that yeah, the process is in control. The process goes out of control if any of these data goes beyond these upper or lower limits, or even if the process starts moving towards, starts drifting towards one side, even then we stop and we check if there is something wrong with the process. So this is of course the control charts for of variable control charts of mean. Similarly, we can draw the control charts for range. We can take the range here, we can calculate the range of the data here. As we know, range is the difference between the maximum and minimum. So what we do is we take the maximum of these four and minus the minimum value of these four, and similarly we can calculate the range of all of these. Then we will calculate the total value of the range. Yeah, of course it will not be called as X bar, it will rather be called as R bar and R bar bar. So the central line now will be 0.29, and about calculating the upper and lower limits, of course we have got a formula for which we need the chart. Yeah, so these are the factors we have for the X bar chart and for R chart. So we will be using these factors in fact to calculate our upper and the lower limits of our chart, and the formula for this is given by the central line. Let me give you the formula here for our chart. The central line is at R bar. Of course since we'll just have R1 bar, and the upper control limit is given by D 4 times R bar, and the lower control limits are given by D 3 times R bar. Okay, again it can be calculated and drawn in the same way. So let's go to the chart and see. For sample size of 4, the D3 value is 0 and D4 value is 2.28. So 0 and D3, of course N is 4. We have let me do right here D4 and D3. Yeah. So D3 is 0 and D4 is 2.28. D3 is 0 and D4 is 2.28. Now to calculate the upper limit is given by R times D4, and lower limits, of course we know it's going to be 0 because D3 is 0. Well, so these are the limits here. The lower specification limit is 0, the upper specification limit is 0.65, and the central line is 0.29. So again we can draw a graph of in the similar way. We will have the lower specification limit here at 0. The upper specification limit will be at 0.6 0.65, and the central line will be at 0.29, and again this time we will be plotting the values of R bar which we have here in the last column. That's all we have in this session. Thanks for watching Edupedia World videos.